Good. Right. So today we've got how many problems here? We've got 6 problems to do, and at least one of them is really bothersome algebraically. But we're gonna try and get through all of these. So the how am I going to explain this? I think I'm gonna want to pull some information from the slides. Give me a second to just pop that open. The key thing about this about these problems, I would say, is actually how do we do this argumentation about the answer being what we claim it to be, which is an absolute max. Like a lot of the steps are very formulaic, but I think that probably the most technical thing that people might be confused by is probably just how that argumentation, that what we found is actually like the absolute max or the absolute min. Like how does that argument work? So I want to try to explain that as best I can. Right. So first of all, if you the first thing to understand is that the typical first derivative test and second derivative test that we learned about from some previous homework, those only tell you local min or max. Okay, whereas the claim that we're trying to establish for these problems is actually about absolute min or max. Those are different things. And absoluteness is actually a statement about like the value being the maximum on a whole domain. Like it's dependent on the domain. This is why like the very first technique that should come to mind for you is going to be this thing that we're calling the closed interval method. So if you have a closed interval, if your problem intrinsically has some closed interval that you can use where like, where's my cursor? From A to B, and you can just plug in f of A, plug in f of B, plug in f of the critical points, and you can just see the values and you can just see like, okay, here's this maximum. You can then conclude that that's an absolute maximum on that domain. And that will completely answer the problem. Like that's one way of justifying it. Another thing that can happen is what's called the, let me see, first derivative and second derivative. Okay, so I'm going to just copy, I'm just going to copy these little theorem blurbs that are like in the slides. And I would encourage you to like stare at them for a bit and think about them. So the first derivative test is pretty much what I said just now. It's pretty much just using this closed interval method, kind of almost. It doesn't, so this one doesn't specify the interval. I mean, okay, no, I'm wrong. The way it works is like these two theorem statements are about already what happens if you don't have a closed interval. So if you don't have a closed interval, then you want to start using these kinds of statements. So your justification ends up involving either this first derivative test for absolute extremes or the second derivative test for absolute extremes. What they're about is, if you read this carefully and then you look back on the first and second derivative tests, just the usual version of them. So there's like just an additional condition in these absolute extreme value ones that guarantees what you're looking at is not just a local min or max, but as an absolute min or max. And that key difference is what we're looking for here. What it's saying is, so for this, it's about this allness here. So if you look at the first derivative test, it doesn't specify precisely like this kind of thing where like the derivative is greater than for all and then less than for all. Instead, the first derivative test usually is just a local kind of property. So like this kind of local behavior around this critical point C, let's call it, that corresponds to being a local max. And the idea is then what happens if this is true and there's like no other critical points. These statements about this for allness just means basically that there's no other critical points to consider. It doesn't ever hit zero. It doesn't ever go and flip in sign. In that case, then really the picture you have in mind is that this really is just kind of like a parabola kind of shape. Like around it, it's always going down. And so that's why this you can claim that the local max is actually an absolute max because there's no um changing in the kind of behavior of that first derivative. And second derivative test is also very much like the same kind of thing. So notice it's again saying something about this for all kind of nature. When we talk about the for all, we're talking about for all x in the domain that this property on the second derivative holds. Trying to recall exactly the statement of the second derivative. Yes, yeah. So the previous version of the second derivative test is one um, where we just tested, I think, where we just tested on the critical point. We took our critical point, we plugged it in, and then we just said like, oh, is the derivative less than or is it greater than? Which is it's a local property. It's a property only on that point. But this statement, this theorem, second derivative test for absolute extremes, is talking about for all x on this domain. So it's not a local property anymore. It's a global property that applies to the entire domain. Yeah, you're stating that that second derivative is always less than zero for the entire interval. And again, that's what that's really kind of saying geometrically is that the whole function is shaped with a negative concavity, meaning like it actually does look again like that kind of parabola shape. So that these are two of the ways, and I believe there's one more. Is there one more way? Okay, it doesn't give you one more way. I guess, yeah. There's these two ways, and then there's the closed interval method. So these are the three um, techniques, these are the three approaches that we can use to justify the claim that once we've done all the calculation work to um, taking the derivative, setting equal to zero, solving, finding the critical point, when we've done all of that, we then have to make that claim about being an absolute max. Like, why is this thing absolutely the maximum, absolutely the minimum? And we have to use these methods. So hopefully I've explained that well. I'm not sure, but I don't know. Let me know if you're confused. So with that said, let's get started on the problems. Right, so we have price, we want to maximize revenue. So the first thing to note is that this, we want to maximize revenue. So our function is going to be some revenue function. And revenue in terms of price, that's just the number of items sold times the price that you're selling them at. So that is just going to be x times p of x. And so the actual function we're trying to optimize is 75x minus x cubed over 4. Okay, and so now we just go through the standard process of optimizing this thing. Take its derivative, 75 minus 3 over 4x squared, and then we would set this equal to 0, and we would solve. So now let's see, bring that over, then we're going to end up dividing by 3 multiplied by 4, we get 100 is equal to x squared, and so therefore x is equal to plus or minus 10. And then we would right away be able to get rid of the negative solution because that makes no sense in the context of this problem. X is a price, or is it a price? No, it's a number of cakes. You're not going to sell negative number of cakes. So you would get to this, okay? And well, it's a critical point, but what kind of critical point is it? And also, is it absolutely what we are claiming it to be, which is an absolute maximum? Well, let's see. What can we do? Hold on. Something is. What did I do here? Oh, okay, I get it now. All right, yeah. So what I try to do was well, first of all, as I typically do, I try to draw a number line to understand or to visually see how my problem works. Okay, so with this number line, that's corresponding to the usual first derivative test. So with the first derivative test, the usual one, we can say that this is a local max. Okay, now that's not good enough, right? It's a local max, but is it an absolute max? So we need to do a little bit more. And mm, what I did was I tried to find a natural kind of interval, a closed interval, so that I could just apply the closed interval method. Okay. And what should occur to you is like definitely one of the endpoints is obvious. Okay. If you sell 0 cakes, you're gonna get $0. That's gonna be the natural endpoint. Like we can say R of 0 is going to equal 0. But then the other endpoint is a bit less clear. How do we figure out the other endpoint that we would want to test on? And then obviously we want to also test on R of 10. And the idea should be that R of 10 is going to give you some positive revenue, whereas this other endpoint will give you zero revenue, just kind of like the typical thing that we saw with degenerating a rectangle in like this previous section. Well, what we can do is we can force it's sort of like for the x equals 0 case, we force this x to equal 0. What we're going to do to find the other endpoint is we're going to try to force p of x to equal 0. Okay, so let's try to force that to happen. So if we want to make px equal 0, that's going to be the same as saying that x squared over 4 must be equal to 75. And then that's 3 times 4 times 25. That's 300 is equal to x squared. And so x is going to be equal to 10 root 3. So if you plug 10 root 3 into the original function p of x, you're going to get back 0. And so that is the endpoint that we would kind of construct. That's kind of the natural endpoint that makes this problem easier to just answer. So we have 0 and we have 10 root 3, and we can apply closed interval method to that, and just plug 10 in to the revenue function. We'll get 10 times. Did I actually plug this in by hand or not? I don't know. It's a bit 75 minus. Okay, I can do this in my head. 75, 100 divided by, so that's 25. So I get 500. Yeah, that's what I'm supposed to get. Good. $500. Okay. Okay. So because we got a positive value and because we use closed interval method, like we can now justify that this is an absolute max, and 10 is what's going to make the absolute max happen. So what is this problem actually saying or asking us for? It's asking us for the cake price. So, okay. Okay. Maybe so we probably phrase this like what cake price will maximize revenue? P is the price in dollars per cake that a vendor can charge. They want to sell X many cakes. What cake price? Price of something's funny here. Hold on. Yeah, okay. I see. It's asking for the cake price, but I have things in terms of revenue. So this value is revenue and X is 10. So actually the price is going to be 50. Price of 50 per cake will maximize revenue by the closed interval method. I'm just going to abbreviate that for sake of time. All right. So that was the first problem. I just wanted to make sure that I got through that as thoroughly as possible. Did that make sense? Any questions? Okay, got a thumbs up. Very good. All right. So this is very much like the easiest problem that we can see. And then the rest, I think, end up being processes are kind of the same. It's just now we have some more algebraic things to deal with. So with 7, this is a triangle. So we've already got square roots going on here. All right, so we're trying to find a triangle or maximize the area of a triangle whose hypotenuse is 1. So what we're going to do is we're going to call one of these sides x, and then we'll use the Pythagorean theorem to say that the other side has to be 1 minus the square root of x, or square root of 1 minus x squared. I wrote it correctly. Okay, and what we want to maximize is the area. So we're going to need an area function. Okay, well, that's 1/2 base times height. And you can see why I don't like this, because I'm going to have to take a derivative of this function to optimize this guy. It's going to involve a product rule, and it's going to involve all square roots. But what can I do? That's the correct thing to do, so I have to do it. So let's just do that product rule. X and then 1/2 radical 1 minus x squared multiplied by a negative 2x. Yeah, I'll put that in parentheses. Okay, so let's see. We can certainly cancel that, but then nothing much happens to this. And this is where I want to say, like, do a little bit of algebra. And what you'll get, can I just say do a little bit of algebra? I would hope so. I guess for this one, I'll just show it maybe. I would pull the 1/2 out, and then notice, like, I can kind of put a common denominator on both of these terms. I can put like the square root of 1 minus x squared. So if you really can't follow the algebra, I would say, like, you should ask me or ask someone during help session to go through it with you. But if I have the time, I can try to do them. I just want to make sure also I get through everything. So this is going to be plus an x squared. Like, the other term is going to contribute a x squared. But I have a minus here. Oh, that's because there's a minus there in that term. So this is a minus. Okay. I only canceled the 2. I didn't cancel the minus. All right. So then this is actually 1 minus 2x squared over the square root of 1 minus x squared. And what are we trying to do? Well, optimization process is just take the derivative, set equal to 0, and solve. We're trying to solve this guy and to find the critical points. Okay. Well, so when you solve this guy, you get x is equal to plus or minus 1/√2. And x being a side length, you're not going to use the negative solution, right? But now also notice that there's a technical consideration here as well, that there's also a critical point of when this thing's undefined, not just equal to 0. See, I can make the derivative or denominator. I can make the denominator equal to 0 by just letting x be 1. So when we say draw our sign chart, we will have to include that at x equals 1. And what I would do, actually, if we also just stare at this picture, you'll realize that there's a very natural interval, because we will make our triangle degenerate if x is 0 or if x is 1. And so the way I denoted that in my thing is I use these little square brackets to actually kind of indicate the extent to which my domain can possibly make any sense. And 1/√2 lies in between 1 and 2, or 0 and 1, sorry. Right, so you can hopefully see that, like, if I make it 0, everything goes to the vertical direction. If I make x equal 1, everything is in the horizontal direction. I don't have a triangle, right? But otherwise I do. So by that kind of reasoning, we can, and also if you just, like, I don't know, plug into a of x, you can then just do the closed interval method very quickly. So a of 0 must equal 0, a of 1 must equal 0, because those are convenient values. But then if I calculate a of 1/√2, which probably want to show a little bit of calculation work, make sure you can do that by hand, but you'll get 1/4. And so what is this problem asking us to do? Maximize the area. find the maximum area and then justify why it's an absolute maximum. So this is the absolute max area, and justification would be by the closed interval method. Okay. So hopefully that made sense. Let's continue. 8. Right. So we have a box with a square base, an open top. We're given the amount of material. So, well, just like I normally do, I would draw a picture, make sure I understand what I'm thinking about. So if it has a square base, something like this, maybe not very good at drawing. X by X, and I would probably say by H. Okay, so this 12 square feet of material is corresponding to the surface area of this without the top. So we can just create a little formula for that. So it's going to have X squared, and it's going to have 4 copies of the sides, so 4XH. Okay, well, if we can, what this is going to give us is going to give us a relationship between the variables X and H, meaning we'll be able to sub one in for the other. What we actually want to maximize or optimize is the volume. We want to find the maximum possible volume. Well, to start off with the volume, if we just think about this naively, it's going to be X squared times H. But to optimize this, we need this to be a function of one variable. So we need to get rid of one of these variables. So that's where the surface area thing comes into play. All right, so I want to then solve this for H. 12 minus X squared and then divided by 4X is going to give me H. Okay, and so now I can replace H by that, and I'm going to get a function for volume in terms of just one variable X. Let's see, if I multiply this over, we're going to have X cancel, but we'll have an X on top. So I'll just, I think I'll do that in one go. So we would end up with this. And well, in order to take a derivative, it makes sense to simplify that a little bit. So, okay. So we would get that. And now we can just go through that optimization process, take the derivative, X squared set equal to 0 and solve. So if I move that over, I'm gonna end up dividing, well, I'll just write it. 3 over 4x squared divide, multiply, get x is equal to plus or minus 2. And so x is equal to 2, right? We only want that positive solution. This is gonna be feet, okay. Right, so this is our critical point. We can do a first derivative test, like the typical first derivative test, just to like make sure that this is a maximum, a local maximum. Let's see, what else can we do here? Well, I can make things, can I make, well, first of all, can I make this degenerate? I think yeah, I can make things degenerate. If I let x be 0, I can make all the sides kind of collide into each other. I can still sort of, it's a bit hard to justify that I can force that the surface area still doesn't fail, actually. That's a bit harder to justify. I don't like that. But what is true is that v of 0 is equal to 0. So I am going to put that down just because v of 0 I can directly see is going to equal 0 if I let x be. If I let x be 0, I can easily calculate what the volume of that would be. We would also want an upper value. So how did I do that? How did I do that? Oh, max out the base. Yeah. Okay. Yeah. So now what if what if the surface area was all incorporated in the base? So you have it so like H ends up being 0. Yeah. Again, you degenerate the rectangular prism, but instead of degenerating the length and width, you instead degenerate the height instead. So um, that is going to occur by just making the base have 12 square feet, which means that x must be the square root of 12, which is going to be 2 radical 3. Yeah. And so if we just write that down, 2 radical 3, that's also going to equal 0 because we have a degenerate rectangular prism versus v of 2, right? And I guess another thing we could have done is actually just put like the plus and minus situation here. Um, Okay, so this is our first derivative. If we use a higher value, this would be negative. This would be negative, that'd be positive. So we have a local max, right? So we can see it's a local max. And closed interval method will tell us it's an absolute max. We actually we don't fully need those signs. I just put them there to help illustrate. But yeah, so plug 2 into my volume formula. I'm gonna get 6 minus, I'm plugging into this version, this 3x minus x cubed over 4, because that's the thing I can plug into. 8 over 4, so that's 2. So I'm gonna get a volume of 4. Just double checking, yeah, 4 cubic feet. And this is the maximum of all 3 things. And so this is the absolute maximum by the absolute max volume by that closed interval method again. Okay. Right. And so now you hopefully are pretty happy with closed interval method, and we can use it again for 10, but it looks like both 11 and 9 do not, for numbers 11 and 9, it's not possible. We have to use one of the other approaches. Okay, so let's go through this. So again, we have a rectangular prism type thing. We have a square base, just for convenience, I would say. Yeah. Okay, whatever. With a volume of 8 meters cubed. Okay, so notice that now there's a difference. So the difference here is from 8 to 9, right? 8 told us the surface area, and we were trying to optimize the volume. Now we're given the volume, and we're gonna end up trying to optimize a weighted version of the surface area, and this makes a difference. Okay. All right. So the material for the base costs. So let's use a function for cost. We're just going to call it C right now. I'm going to use the same variables, X's and H's. The base is going to cost $1 per meter squared. So the base is going to contribute X squared times 1, let's say, for the cost. And then plus $4 per meter squared times the fact that we have 4 sides that are of the same size, X times H. Okay, so we're trying to optimize this X squared plus 16x H. And we know from this statement about volume that X squared H is equal to 8. Well, just like before, we will be able to replace out the variable H with X. So H is equal to 8 divided by X squared. And so now we can replace that away. Let's see what we get. 16 over, or well, not 16 times 8. So I should know what that is, 128. I'll just write that's 128. Yeah. And so now we have a function for the cost, and we're trying to optimize that. Well, by minimizing. All right, so we want to minimize cost. Okay. So the problem here is that if you just reason about the interval, the only thing you can conclude is that x is going to be in 0 to infinity. X can't be negative. It shouldn't be 0, but it can be as close to 0 as you want it to, because you can just have some absurdly high value for age, with age x being really small, and you'll still be able to make the volume of the rectangular prism equal 8. Like that's still going to be possible, so no matter what value. And if I want x to be really, really large, I can make x be really, really tiny, and I'll still be able to balance things out and make the volume equal 8. So that's why this is the natural interval for x, and that's why we need to use a different approach. We can't use closed interval method here. Right. And so let's see what we can do. Well, we just like normal, we would still try to take the derivative, set it equal to 0, solve, try to optimize this thing. 128 over x squared is going to be what you would end up getting. When you try to solve this thing, I would say that the better technique to use is not the better technique is actually to try consolidating the fractions on the same side. Normally, you're taught to like take this fraction, move it to the other side, multiply by x cubed. The problem is with that multiply by x cubed. People are just going to do that, and then they're not going to realize that implicit in that is an assumption that x is not equal to 0. Okay, so I think that it makes it more obvious if I modify the left-hand side to bring everything into one fraction. And then we see implicit in this guy is the fact that x cannot be equal to 0. Okay. And then we end up with x cubed minus 64 equals 0, which tells me that x must be equal to 4. The reason for that 0, I guess, is when we draw the critical points, when we would normally do the sign chart, we would have to include that 0. Otherwise, the sign chart could be kind of off, I guess. Maybe you don't need that. I'm not quite sure. But regardless, this 4 is definitely a critical point. And you can see like, oh, this looks like a local min. Okay, but how do we argue? It's definitely a local min. But how do we say with certainty that this is an absolute min? Well, the easiest thing here is actually to use the second derivative test. So I guess that's a good reason for why we explain this more complicated method to use, because this will help to shortcut things. Or I suppose like what you could kind of use the first derivative test as well, because if you only look on this interval 0 to infinity, you only look here, you exclude out that critical of 0, and you see like, oh, there's no other sign changes, there's no other critical points. So you could use the first derivative test. But what came to mind for me, at least, more was the second derivative. So let me show you what happens. If I take the next derivative of this, the sign is going to change again for this other term. So I'm going to get 256 over x cubed. And the key thing here is that this is always positive. Well, for x being a positive number, this is always going to be positive. Okay, so because this, if you just scroll back up to what is the statement about this second derivative for absolute extremes, the second derivative is always either positive or always negative for x in that interval. Then what you have is an absolute max or min, whichever one you're looking for. All right, so this allows us to conclude that x equals 4 is going to give us an absolute min. But I think that what we were trying to solve for our dimensions. Okay, so we want okay, yeah. So x equals 4 is going to correspond to giving us an absolute minimum for cost, for the cost. And then the reasoning is by the second derivative test for absolute extreme values. I would write everything just to be as technically correct as possible. Dimensions, you can plug those in and you'll get 4 by 4 by a half, and these are in terms of what? Meters. Yeah, because x is equal to 4, so base is 4 by 4. Height is going to be the thing that makes the volume equal to 8, so half. Okay. Any questions? Did that process make sense? No questions? Okay. Right. So 10 is a pain. 11 is actually easier than 10. But we'll go through the 10. Because if you're doing 10 correctly, showing all of your work, you've got lots of pies floating around. 10 feet of framing. All right, so let me do it like this. I called this guy X. Like I called the horizontal length of it X. I called the vertical length of it Y. So it's important that this thing that looks like a square is actually not a square. It's a rectangle instead. And I think we'll need to consider the half circle as well. So radius is 1/2 X. We only have 10 feet of framing, so that is about the perimeter. So this is actually equal to X plus 2Y, and then plus, well, half of the circumference of a circle, so 1/2. So for circumference of a circle is pi times the diameter. So we can actually just think of this as 1/2 of pi times X. Okay. The thing we're trying to optimize is we want to maximize the Windows area. So the area is X times Y plus half of pi times the radius squared. So that's going to be 1/4x squared. All right. And so this is where we've got quite a bit of algebra to do. Which I want to shortcut somehow, but I have to figure out how I can shortcut it in a way where like you can fill in all the details. Because notice like this, in order to do anything with this, right, the idea is we're going to use this equation to get rid of one of the variables. Probably y. Yeah, we want to get rid of y. Yeah. Well, I'll just write down what that substitution will end up being. So if you do a bit of algebra, you're going to get y is equal to 5 minus pi over 4 plus 1/2 x. And I do use that. Yeah, I do. Okay, so with this area formula, you can just clean that up a little bit. So that's pi over 8x squared. And then when we replace in the y, let's just jump through that because I really don't have enough time to go through all the details. But fulfill in all the algebraic details, and you'll get this as your function to optimize. Pi plus 4 minus pi plus over 8, and then x squared. Yeah, so that's what you get. And well, we take the derivative, set equal to 0, and solve. Okay. 5 minus pi plus 4 over 4 x, set equal to 0. Solving that is going to give me 20 over pi plus 4 is equal to x. Feet. Yeah, so this is what we would claim to be, well, this is the critical point that we get, and naturally what we would think is like this should correspond to maximizing. We just have to argue that that is the case. Well, notice that this first derivative is really easy to deal with. We can just take another derivative, and it's just so easy, right? We just use the second derivative test for absolute extreme values. So take another derivative, and we're gonna get negative pi plus 4 over 4, and that's negative, right? Which allows us to conclude that that value that we found above is an absolute max. And it's by the second derivative test for absolute extreme values. I'm abbreviating for sake of time, so sorry. Yeah, and then last thing that it wants is it actually wants the dimensions of the window. So I think not only do you need the x value, but you need the y value. So what you do is you take this value boxed and you plug it into this this equation up here. And that's just, and then you calculate what that value is. So there's more algebra that you do, and eventually you end up with y is equal to 10 over pi plus 4 feet. So yeah, should make sure that you can do that calculation as well. And then these two things, well, they should be the dimensions that the problem is asking for. Okay. Right. Lastly, 11. We have 5 minutes. Yeah, that should be fine. So weight is given by some formula here. We want to find the values that minimize the cost of raising a hog of this weight. Okay, so that's W. If corn costs 6 and minimize the cost. Okay, yeah. All right. So yeah, what this is saying, 250 is equal to 50 x to the 1/2 and y to the 1/4. So and it says something about cost. So cost is 6 per 100 pounds. Notice that, is this written in terms of hundreds of pounds? Yes, yes. Yeah, so X is hundreds of pounds, Y is hundreds of pounds, and these are in terms of hundreds of pounds and hundreds of pounds. Great. So 6 times X plus 15 times Y is going to correspond to the cost function of our situation. And just like, everything else, we want to get rid of one of these variables. So that's why we use the first equation. Divide by 50, we're going to get 50 is equal to x to the 1/2 power, y to the 1/4 power. Then what I want to do is I want to actually raise both sides to the 4th power. That's going to get rid of the square roots that happen. Really, you can think about this as squaring it twice. Wait, is it not 50? It's not 50. It's 5. Yeah, divide by 50, get 5. So you can think about this as squaring twice. If you square it the first time, you're going to get x times y to the 1/2 on the right side. You square it one more time, you're going to get 625 is equal to x squared y. And that's really useful because we would rather not deal with square roots, right? All right, so now the easiest thing is to get rid of y in this case. So I'm going to then move things around. 625 divided by x squared is equal to y. So I can then replace out the y in this equation. 6x plus, I did actually calculate that. It's a bit funny. Well, yeah, it's fine. I'll just, yeah, I definitely did not do that by hand. Whatever. So, over x squared. And so this is now my cost function. I can then optimize it. Plus that's going to be a minus actually. And it's going to multiply by 2. Okay, that I didn't bother to do. So minus 9375 times 2 over x cubed. which we can imagine setting that equal to 0 and solving. Jump a few steps, let's say, and this is going to give us that x will be equal to 5 times the cube root of 25. And then I also calculated y. I'm thinking that the reason is because the problem asks us for it. Yeah, find values of x and y that minimize. So yeah, this value of x is going to lead to y having the value of the cube root of 25. And again, like that's yet another computation that you need to maybe fill in the details if you're trying to show all your work on paper. Right, so then the statement you're trying to show is that these correspond to the answer, and you need to now justify this is actually minimizing the cost, like this is actually the absolute minimum. Well, it's nice that this is just a 6, because I know if I take a derivative, that's going to disappear. And then what's going to happen over here? Well, the sign's going to alternate again, and so I'm going to have something that's positive, a number over x to the 4th. Okay, well, that x to the 4th is going to help me to conclude things. So I know that taking yet another derivative is going to make things a little bit easier on me. Well, but I'm again not going to care about numbers. Didn't even need to write down 73. So I could just did like 625 times 15 without actually multiplying that out. All right, so you get this. So the second derivative is this number, or not this fraction. And well, this is always positive for x being actually just, well, for all x, really, for all x except for 0, because you can't plug 0 in. But yeah, for all x, that's positive. And so that will help us to conclude it. This tells us that the configuration that we found is an absolute minimum. It's going to correspond to an absolute minimum for the cost function. And we know that by the second derivative test for absolute extreme values, abbreviating once again. Yeah, so I think that's, I explained that problem completely as well. Okay, so we're a bit over time, but I just want to stick around and answer any questions if you have any. So is there anything in this set of homework that didn't make sense to you? I see 2 thumbs up. Okay, that's good. All right, well, if no questions, then we'll stop here.